we're going to use several methods to try to figure out the identity of an unknown molecule. And so many of those are spectroscopy. Spectroscopy is a set of methods based on the interaction of energy and matter. And the energy has to be the specific wavelength. And there are many types of spectroscopy. Each of them gives us some information, and if we put them all together, we can figure out the structure of a new compound. So let's take a look at the common types of spectroscopy. Ultraviolet visible, UV-Vis, and infrared, it's easy to tell what types of electromagnetic radiation they use. NMR, nuclear magnetic resonance spectroscopy, uses long radio waves. NMR, even though the word nuclear is in it, it's not radioactive. We're not doing any radioactivity. We're dealing with the nuclei of certain atoms. We've already talked about mass spectrometry, measuring the mass to charge ratio. And if we use X-rays, we can use X-ray photoelectron spectroscopy. We're actually going to talk about that much later in the year. That gives us information about the number of electrons in a specific orbital. All right, so let's start with looking at electromagnetic radiation and how it interacts with molecules. This is not a chart that you need to memorize, but you should know that the longer wavelengths are radio and the shorter wavelengths are ultraviolet. We'll take a look at that later. UV interacts with the pi electrons in a molecule. We'll talk about what a pi electron is well, I'll tell you now. Pi electrons are electrons in p orbitals that are involved in bonding. Visible interacts with conjugated pi electrons or d electrons, electrons in the d orbital. We'll talk about what conjugated is in just a minute. We're going to take a look at infrared spectroscopy, where the bonds in molecules can stretch or bend. And we'll take a look at NMR, which changes the state of the way a nucleus is spinning. All right, so pi electrons, if you think about a molecule and it has a double bond or a triple bond, it is that second or third bond. Those are bonds made up from p orbitals. We're going to come back to that more in a little bit and later this year. All right, hopefully you have seen this chart somewhere before. High energy corresponds to short wavelength. Things like X-rays and gamma rays are very high in energy, very short wavelengths. Ultraviolet and visible are often in the nanoscale. We're going to focus on visible. You need to know that ultraviolet is higher energy than visible and that visible is higher energy than infrared. You should also know Roy G. Biv, and that violet is close to ultraviolet and infrared is close to red. So if we have low energy, we have long wavelengths. So long wavelengths would be something like the radio waves just that are used for NMR. All right, let's take a look at a spectrometer. First, we have light going in, and we only want a narrow band of light, so we put it through a narrow slit, and then we want to separate all the wavelengths out. So we use something called a monochromator. It's like a prism. So it separates the electromagnetic radiation into all its different wavelengths. We're only interested in one wavelength at a time. So we go through a second slit, and then it goes through the sample and a detector. Only certain wavelengths can cause changes, and that's what we're going to measure. That's what we call something that is quantized. So possibly something at 450 nanometers will cause a change, but something at 470 nanometers won't cause a change. They're detected and they're recorded. So we have light, narrow beam, split it into wavelengths, single wavelength at a time, passes through the sample to the detector, and then we record it. Now, our visible spectrometers actually work a little more differently than this. Ours are more modern, and so they can actually hit all the visible wavelengths at the exact same time and have the computer sort out all the information. So in the olden days, it used to take us an entire class period to get a spectrum of a bunch of different visible wavelengths. Now, it takes about 2 seconds. All right, let's go back to UV-Vis spectroscopy. What happens is the valence electrons go from their energy level to a higher energy level. And energy is required to do that, so the light is absorbed. If there's a long conjugated system, it's lower in energy, so it can absorb visible light. So we will, if it absorbs certain colors, other colors pass through, and that's what we see. So now's a good time to take a look at the little video about the colored flowers. Now that you understand a little bit about conjugated molecules, let's take a look at them in more detail. Here we have 3 conjugated molecules, a little conjugation. This is more conjugated, so it would absorb at a higher wavelength, or sorry, a longer wavelength. And this is even more conjugated. This is blue dye. And so we have alternating double, single, 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 double, and we can go this way, single, double, single. So alternating large enough that the absorbance has shifted and we see blue. That's how phenolphthalein works. Phenolphthalein is a colorless compound. You saw that when it was in the KHP solution. And when you add base to it, you remove the 2 hydrogens on the alcohol groups. That actually changes its structure so that we have O is now double bonded to the carbon, which is single bonded to another carbon, double bonded, single bonded, double bonded, single bonded, double, etc. So this absorbs some blue wavelengths, letting us see the pink wavelengths. And here is another example of how conjugation changes the absorbance. Here, I have 1,3-butadiene, 2 double bonds. So it's double, single, double, and it absorbs around 217 nanometers. If instead I have something that has a benzene ring alternating double, single, double, single, double, single, single, double, it's more conjugated, and the absorbance has shifted towards a longer wavelength, lower in energy. There are certain proteins that absorb at 280 nanometers, certain amino acids, sorry, and if they know how its absorbance, people can actually calculate how many amino acids of tyrosine are in that molecule, that large protein. All right, let's talk a little bit about the colors we see. The transmitted light, the light that passes through, is the opposite of the color that's absorbed. And the color of light is related to the energy of the transition. So if there's only a little bit of distance between the lower and higher energy levels, it's low energy, long wavelength, towards the reddish region. If instead this electron has to move a lot to get to the higher energy level, there will be a high energy photon or short wavelength. And as I mentioned before, only certain wavelengths can work. It needs to be the exact wavelength to jump from the low energy to the high energy level. If it's not the exact right wavelength, nothing happens. That's what we call something that is quantized. All right, let's take a look. This is not, again, a table you should memorize, but if you know the approximate wavelength, the approximate color of light, you need to know the order, and you need to know that violet is shorter, red is longer. The complementary colors are what pass through when a certain color of light is absorbed. So here we have white light going through, but it's a blue solution. So if it looks blue to us, then it must mean that orange light is absorbed, or the colors other than blue. The solution looks blue. If purple light is absorbed, or maybe reds and purples, the solution will appear to be yellow. And you saw that in the little video about the flowers. All right, now I want to get a little more quantitative. So take a break if you have to. Let's take a look at this. The intensity is how much light reaches the detector. So the first thing we do is we measure a blank with no sample in it. And we measure how much light reaches the detector. That's the denominator. The numerator is the amount of light that passes through the sample at a specific wavelength. And so we look at that ratio with a spectrophotometer, and that's called transmittance. Typically, we express it as percent T or percent transmittance, which is transmittance times 100. So here we can see at 100% transmittance, all the light passes through. At 0% transmittance, no light passes through. So in this sample, the purple light passes through and the greenish yellow pass through. And at 694, that little blip means that some of the ruby laser passes through. Now, transmittance is how the machine operates, but absorbance, which is the negative log of transmittance, is actually more useful to us. It makes a nice graph of absorbance versus wavelength, and at the top of the peak, the highest peak, that wavelength, so if we read the wavelength right here, that wavelength is lambda max. Lambda is the Greek letter L, and it stands for wavelength in chemistry and physics. So we can find the maximum wavelength. And once we find the maximum wavelength, or sometimes we might even want a different wavelength, we can measure the absorbance versus concentration. So we take a bunch of solutions of varying concentration, we know their concentration, and we measure their absorbance, and we make a graph. The slope of the line is the absorbance divided by the concentration, and if I end up with some unknown solution, I can just put it in the machine, read its absorbance, and figure out its concentration. So that's really useful for figuring out the concentration of some unknown colored materials. It doesn't work for colorless because, keep in mind, all the light passes right through. Now, we actually have an equation to deal with that. It's called Beer's law, named after the person, not the drink. And so if we measure the absorbance, it is the molar absorptivity constant or extinction coefficient, depending on which book you're looking at, times how far the light has to go through the sample. Our machines, it's 1 centimeter, times the concentration. Anything with a logarithm is unitless. So because absorbance has no units, we have a unit of centimeters here and molarity here. A has to have a unit of liters per mole centimeter. Now, if we look back at what we saw before with slope, slope is absorbance over concentration, which is the molar absorptivity times path length, and for us, path length is 1. So it's really easy to find this constant by just graphing absorbance versus concentration. So let's try a couple of problems. Here, I have a spectrometer with a 1 centimeter path length, and other people have measured the molar absorptivity. So I want to predict the absorbance of a solution. So I know that the absorbance is little a times b times c. Note that molarity to the -1 power, centimeter to the -1 power, is the same as liters per mole centimeter. So all I have to do is plug these numbers into the calculator, and my absorbance should be about 0.30. I can also find percent transmittance. If A is negative log T, negative A is log T, so take 10 to the both of those. 0.3 was my absorbance, so 10 to the -0.3 is my transmittance. So I have 50% transmittance. Pause the video and try this problem. Okay, let's take a look at the answers. In this case, I want the absorbance when I have the transmittance, 0.21. And now that I know the absorbance, I can calculate the concentration. Okay, so that takes us through UV-Vis spectroscopy. We're going to focus mostly on visible because our spectrometers are visible. Good luck trying the problems.